Have you ever stopped to wonder why you can see your reflection in a calm lake, but not, say, on a piece of paper? Or how about this one? Why does a straw in a glass of water look like it's completely bent out of shape? Well, it all comes down to the absolutely fascinating physics of waves. And in this explainer, we're going to unpack how these invisible forces of light and sound literally shape the world we experience every single day.
So, here's our game plan. We'll kick things off with the absolute basics, what a wave actually is. Then we're going to explore the incredible electromagnetic spectrum. After that, we'll see what happens when waves run into things. First, how they bounce off, which is called reflection, and then how they bend when they pass through something new, which we call refraction.
All right, first up, we need to get right to the heart of it all. What in the world is a wave?
Okay, if you remember one thing, make it this. Waves move energy, not stuff. It's a super important distinction. When light travels from your phone to your eyes or sound travels from a speaker to your ears, there aren't any physical bits flying across the room. Nope. It's just a disturbance, a pulse of energy, rippling through space or the air.
Now, what's really cool is that waves basically come in two main flavors, and it all depends on how they vibrate. You've got transverse waves, like light, which wiggle up and down. That's perpendicular to the direction the energy is actually moving. A great way to picture this is a ripple on a pond. Then you've got longitudinal waves, like sound, where the vibrations compress and expand in the same direction the energy is traveling. They're parallel. Think of a slinky being pushed and pulled from one end.
So to talk about any kind of wave, we use a few key terms. First is amplitude. That's basically its height, or you can think of it as its intensity. Then there's wavelength, which is just the distance from one peak or crest to the very next one. And finally, you have frequency, which tells you how many of those full waves pass by a certain point every single second.
Okay, now let's zoom in on one of the most important families of waves in the entire universe, the electromagnetic spectrum.
And get ready for this, because it's just mind-blowing. Every single wave in this family, I'm talking everything from radio waves to gamma rays, travels at the exact same unbelievable speed through the vacuum of space. And that speed is 300 million meters per second. It's pretty much the universal speed limit. Nothing's faster. And here you can see the whole family laid out. Over on the left, you have long, low-frequency radio waves. And as you move to the right, you get all the way to the super short, high-frequency gamma rays. You'll notice this inverse relationship, right? As the wavelength gets shorter, the frequency and the energy gets way, way higher.
But here's the wild part. Our eyes can only pick up this tiny, tiny little sliver right there in the middle, which we call visible light. And inside that little sliver, all the different wavelengths give us all the colors we can see. And you can remember them easily with good old Roy G. Biv.
Okay, so we've got a handle on what waves are and the different types. But this is where things get really dynamic. What happens when a wave that's cruising through one material, like air, suddenly hits a boundary with a totally different one, like a pane of glass?
So yeah, what are the options here? When that light ray hits the glass, what's its fate gonna be?
Well, it turns out there are three main things that can happen. The wave's energy can be absorbed by the material, usually turning into heat. It can be transmitted, which just means it passes right on through. Or it can be reflected, bouncing right off the surface. And a lot of the time, it's actually a combination of all three.
Let's really dig into that third option, reflection. I mean, this is the phenomenon behind everything from seeing your face in the mirror to hearing an echo bounce back at you in a can jar. And you know what? The physics that governs all of this is based on one beautifully simple rule. The angle that a wave comes in at, that's the angle of incidence, is always equal to the angle it bounces off at, the angle of reflection. Every time.
And we can actually map this path out with a super simple drawing called a ray diagram. First, you just imagine a line drawn at a perfect 90-degree angle from the surface. Physicists call this the normal. Then, you just measure the angle of the incoming ray to that line and draw the reflected ray at the exact same angle on the other side. That's it. Simple as that.
So, this brings us back to our original question. Why can you see yourself in a mirror but not a wall? Well, it's all about the surface. A mirror is incredibly smooth, so it causes what we call specular reflection. All the parallel light rays hitting it bounce off in the same parallel direction, and that keeps the image intact. But a piece of paper, even though it feels smooth, is actually really rough on a microscopic level, so it causes diffuse reflection, scattering the light every which way so no clear image can form. All right, so that's reflection. Now, let's look at what happens when a wave gets transmitted through a new material. See, it doesn't always just go straight through. Sometimes it bends. This is called refraction, and it's the whole reason that straw in your drink looks like it's broken right at the waterline.
Refraction, which is really just a fancy word for the bending of a wave, happens for one simple reason. The wave changes speed when it enters a new material. For instance, light travels slower in water than it does in air, and it's that change in speed that forces it to change direction.
And lucky for us, there are two simple rules to predict which way it's going to bend. When a wave enters a denser material, like light going from air into glass, it slows down and bends towards that imaginary normal line. And when it leaves and goes back into a less dense material, it speeds up and bends away from the normal.
Now, here's a curious little detail. While all this bending is going on, the wave's frequency, remember the number of waves passing per second, stays exactly the same. So to make up for the change in speed, the wavelength itself has to change. As a wave slows down, its crests get kind of bunched up closer together, which means the wavelength gets shorter.
And this right here is where it all comes together. It turns out that not every wave bends by the same amount. The angle of refraction, how much it bends, actually depends on the wavelength of the light.
So that leaves us with one final thought. We know that white light isn't really white. It's a mix of all the different colors of the rainbow. And we know each of those colors has a slightly different wavelength. So what happens if you pass a beam of that white light through something like a glass prism? And each of those different wavelengths gets bent by a slightly different amount. What beautiful phenomenon do you think that creates?